In this video, I would like to give you an intuition of self-attention mechanism in transformer networks. Actually, attention mechanism is not something new. Attention mechanism has been introduced back in 2014, but transformer networks using attention mechanism was introduced back in 2017 in this paper called Attention is All You Need. It is the beginning of the revolution in natural language processing. Transformer networks such as BERT, Transformer XL, OpenAI's GPT-2 and GPT-3 have been very successful with these transformer architectures. In this video, we're going to focus only on one thing, and that is this multi-head attention and this vanilla transformer network as described in the Attention is All You Need paper. First, I would like to give you an example sentence. The sentence is, I swam across the river to get to the other bank. And the important thing here is, what is the meaning of the word bank here? Is it a financial institution or a sloping raised land, as in riverbank? Of course, in order to answer the question, we have to understand what does this word bank surround itself. We want to identify what are its surrounding words. What are the words which augment the meaning of the word bank? Since we see swam and river in the sentence, this word bank is no longer a financial institution. It cannot be. It may be, but it is very unlikely that it will be. But rather, it is extremely likely that this word bank means sloping raised land. But if you change the sentence slightly differently, in a way that I drove across the road to get to the other bank, then this bank is very likely to be a financial institution. See how things change depending on the context of the sentence. And that's the reason the context is very important to define the meaning of the word in a sentence. However, if I show you this picture before I tell you that sentence, I swam across the river to get to the other bank, what would you think? This is a little bit funny because you might actually think that you actually have to swim across the river or the road to get to the other bank to withdraw your money. And therefore, context really matters. So now we should ask this question: can we build a mechanism that weighs neighboring words to enhance the meaning of the word of interest? Can we build a mechanism in a neural network where we can use this mechanism to enhance, to augment the meaning of a word by allowing this mechanism to look around itself? For example, can we build a mechanism which looks for other words in the sentence and weighs the influence of those other words to the word of interest to potentially change or augment the meaning of the word? Here, we want to augment the meaning of the word bank with two words, swam and river, where the other words might not be that important. So that is the main purpose of self-attention mechanism. Its main purpose is to add the contextual information to words in the sentence. So let's see it in a more tangible example. We're still going to use the same example sentence here, which is, I swam across the river to get to the other bank. The first step that we have to do is to tokenize. What tokenizing actually means is basically chopping up this one large chunk of a sentence into multiple parts. Here, words. So I'm not going to go into detail of how tokenization is done and different ways of tokenizing. Here, just assume that we're taking one word at a time, and each word refers to a token here. However, a neural network does not understand English words or words in any language. We have to convert these words into vectors. So we have to vectorize these tokens. If you're not familiar with vectorizing these words, I would highly recommend you to look up various tutorials and articles and videos on Word2Vec and how those word embeddings are created. I will link to some of the tutorials in the description below. For example, a word vector can be of nth dimension such as 50th dimension. Here, the v1 in the box can be a word vector having 50 numbers. These are all numbers, and those are something that the neural network can understand. And this is what we call word vectors. Word vectors are not just random numbers. They have some semantic meaning associated with it. Words which are of similar meanings or are closer to one another in terms of the semantic meaning, they tend to cluster up as vectors. For example, here I use this awesome project from TensorFlow, projector.tensorflow.org. I use the Word2Vec to visualize first three components of PCA of the word embeddings, and I search the word bank, and I look for similar words near the word bank. So as you can see, it is very close to the word such as monetary, banking, IMF, fund, currency, which are all indicative of financial institutions or something related to money. But that's not all. You can also see certain words like canal, you can see words like river, along with the word which are close to the meaning of the word bank. That's pretty interesting. It is not very close, but depending on the context, we might want to push the word bank closer to these words. And that's an intuition that I want to give you, the first intuition of self-attention mechanisms. How do we push this vector closer to the other vectors which are indicative of water bodies, such as rivers and canals? If this word bank is used in this sentence, I swam across a river to the other bank. So to give you a full overview of self-attention mechanism, the input that it takes are these word vectors, and it weighs word vectors according to the context of that word, and then it provides contextualized representation of vectors. So if your word bank is just extracted as a word vector, it may be closer to financial institutions and things related to money. But after you have added other context in the sentence, your contextualized representation of this vector might be closer to water bodies like rivers and canals. And this is what this self-attention mechanism is actually doing. So let's go step by step. First, we're going to get scores by using a dot product. What are we going to do is we're going to get scores by performing dot products on these vectors. Before I go into that, let me give you a quick recap on what a vector dot product is. So let's say we have three vectors here. We have a vector A, B, and C. As you can see, vector A is closer to vector B than it is to vector C. So what we can say is something like vector A and B are pretty similar. They're closer, so they're similar. So if you do a dot product between vector A and B, you're going to have a magnitude which is larger than if you do a dot product between vector A and C. So that is the essence of a vector dot product. If you do a vector dot product between two perpendicular vectors, for example, if you do a dot product between vector 4, 1 and vector D, which is, let's say, negative 1, 4, then you're going to have 0. The vector dot product between two vectors which are perpendicular to each other is going to be 0. And the vector dot product between two vectors which are completely opposite to each other in terms of the direction, you're going to have a pretty small value, and that's going to be a negative value. So what I want you to remember from this slide is, if two vectors are close to one another, the dot product is going to be big. Or in a way, if two vectors are similar to one another, the dot product is going to be big. So let's go back to this. Let's assume that we have these vectors, and each word vector is of dimension 1 by 50. That is a row vector, and they have 50 columns. So now we're going to do dot product. So how we're going to do dot product is we're going to do dot product for every pair possible, including itself. So first we're going to find a dot product between vector v1 and itself. So vector v1 is 1 by 50, and we have to transpose vector v1, so it becomes 50 by 1. So if you do a dot product, basically what you have is you're going to have this dimensionality agreement, and you're going to have a singular number, 1 by 1, a scalar essentially. And that is a score. We're going to do the same for vector v1 and v2, same for vector v1 and v3, vector v1 and v, like this. And we're going to do for every pair possible. So we're going to have something like this. Essentially, what this means is if this n, let's say, is this last word, what it is doing is this word vector is trying to see which other word vector is close to itself. And if they are close to one another, their dot product is going to be big, and their score is going to be big. That is, they have some form of agreement. That is a very important essence that I want you to get. By doing a dot product between word vectors, we're essentially trying to get the scores. The higher the score, the closer the meanings, the higher the agreement between words. So to put it graphically, it will look something like this. The word is closest to itself. The word I is going to be closest to the word I. The word swam is going to be closest to the word swam, so on and so forth. So the main diagonal is going to be white. Here, white is higher score, and as you go darker in color, the score is lower. I made a mistake here. Actually, this box should be white. So let's see for the word swam, which is the second row. The word swam is supposed to have pretty high score when it is compared to the word river, and when it is also compared to the word bank somehow. So by looking at this graphically, you can have an idea of which words are closer to another. And of course, this half is a reflection of this other half. So this is the first step. Check. Get scores by dot product. And here I put these S1s, S2s, S3s in a little box. It's an abstract representation, but this S1 actually is comprised of S11, S12, S13, so on and so forth until S1n, which is this. So this S1 can be seen as like this. So in graphical representation, it corresponds to this first row, and each element of this S1, which is S11, S12, S13, can be seen as these boxes in this row. So if your score is very high, your S11 is very high because you're attending to yourself, you're doing a dot product to yourself, your score is very high, so it's very white. And if you're not very similar, it's not going to be very white. So this is all driven by these word vectors. It's very important to have very good word vectors as well. Next, we're going to normalize with softmax. Okay, why do we have to normalize? After you have done dot products between vectors, you're going to get these scores. These scores are going to be all over the place. They're going to be very big. They can be very small. The range is going to be pretty unwieldy. So we're going to normalize. So the way we're going to normalize is we want to make sure that if we add these S11s, S12s, S13s until S1 ends, if we add them all up, we're going to get 1. So we want to normalize in that way. And how do we normalize to get that kind of behavior or form? We use softmax, of course. So basically, we want to get weights, because now we're normalizing and we're just going to call them weights. The weights are obtained from scores, And the way to obtain weights is to basically take the softmax of the score. So essentially, if you want to get the W11, take the exponent, the e to the power S11, divided by e to the power S11 plus e to the power S12 plus e to the power S13 dot 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 e to the power S1n. So that is pretty much that. We're all familiar with softmax. And that is how you're going to get W11. And then we're going to get W12, W13, so on and so forth until W1n. So we're going to do that for every other W's as well. They all come from what? They all come from scores. Here I had another typo as well. Sorry about that. This one should be an N. So what do we have? We have weights. How do we get weights? We get weights from scores. How do we get scores? We do dot product between vectors. And now these weights are going to be useful to weigh the original word vectors. What are our original word vectors? Our v's. We have v1, v2, v3 up to vn, and we're going to weigh them. So the way we're going to weigh them is like this. So we're going to multiply this w11 with v1, w12 with v2, so on and so forth until the end of the set. And we're going to do that for everything. So we're going to get these resulting vectors, y1s, y2s, y3s, and yn's. If you're a little bit confused, I'll get to the detail of it in a while with a good example. But remember this. These v's are word vectors. And these w's are the weights that we want to put on this word vector. For y1, this y1 actually is the contextualized representation of v1. So you're going to take some weight from v1, which is yourself. You're going to put a lot of weight. You want some influence from v2, and the influence is defined by this weight. And you want some influence from v3, that's defined by this weight, so on and so forth. So now your word vector is no longer pointing in the same direction as it was before. It is pointing probably in a different direction, which is influenced by its neighbors. The vector is basically tugged and pulled to a direction where it is enhanced by its neighbors. That is the beauty of it. You're using whatever that you had, whatever that your surroundings had, and then you're enhancing yourself. And that is step number 3. You weigh your original word vectors with the weights. So that is the flow of a self-attention mechanism. It is pretty simple. So now if you think about it, you have a sentence, you tokenize it, and then you have word vectors. And these word vectors are practically looked up in a word embedding that you have got from somewhere, probably word2vec or some other word embedding. And you weigh those word vectors according to the context. And you get the contextualized representation of vectors. Here, v1 is the original word vector. y1 is the enhanced version, the augmented version. And how do you augment and enhance? You weigh your surroundings to influence yourself. And the process is first, get scores by dot product, normalize with the softmax function, weigh original word vectors, and there you go. So now I want to give you some more concrete example in a single slide. Let's assume in this example we have only 3 words. And these 3 words are represented by 3 vectors. Word vector v1, word vector v2, and word vector v3. For the sake of this example, let's say we want to enrich the word vector v2. That is, we want to find the contextualized representation of the word vector v2. And v1, v2, v3 are something that are like keys, something that we might want to match up with our v2 to find which key is close to our question, our query. So first, you do a dot product between v1 and v2. you got S21, V2 and V2, you got S22, V2 and V3, you got S23. These are the scores. And what do you do next? You normalize these scores and you get W21, W22, and W23. Remember, we're just only caring about V2. And now we're going to have to weigh original words with these weights that we have got. So how do we weigh them? We just multiply them. Here S21, S22, S23s are all scalar values. W's are all scalar values. And we just multiply this scalar value like an element-wise multiplication with our vectors, our word vectors. So now we have Y2, which is a contextualized representation of our original word vector V2. And I want to reiterate the dimensions. The original word vectors are of dimension 1 by 50, each of them. The vector V2, which is a word of interest, is also 1 by 50, but the scores and the weights are all scalars. And the final word vector, Y2, is also of the dimension 1 by 50. And in this thing that I boxed in, this dashed orange box, is essentially an attention mechanism. Or to be more precise, a self-attention mechanism. But you might have a question, where are all the learnable weights? So far there is nothing learnable here. There are no weights. So where are all the weights? Now we're going to inject something. And pay super close attention here, because this is where we're going to introduce something which has been used over and over again in attention mechanism literature. In the example that I've given you, V2 is something that we are curious about, that we are interested in. Like, my question is V2, as in, which word is closer to my question word V2? Is it the word V1? Am I very close to V1? Am I very close to V2? Am I very close to V3? So this is more like a question or a query in a database term. Well, these are more like keys in database term. So if you have a query, and if your query is exactly matching the key, then all you need to find is the value that the key points to, and then you get the answer for your query. But here these vectors are not going to be exactly the same, so it is nonsensical to actually check with an equal sign, but rather we would want to know how similar they are by doing what? A dot product get scores. So we're going to do a dot product between our query and our key, query and our key, and query and our key. And after we have gotten the weights, what do we want to do is we want to weigh the original word vectors with these weights. And essentially, these original word vectors are in a sense values, because now your result is different weighting that you put on these values. This is pretty confusing and interesting at the same time, and it's the beauty behind this self-attention mechanism. It is using the same word vectors for keys, queries, and values. And that is where we are going to inject our weights. But we don't want to mess up our dimension. That is, we have 1 by 50 here, 1 by 50 here. And if we were going to inject something, we want to preserve the dimension. So we're going to inject a weight here, which is of the dimension 50 by 50. So if you do a matrix multiplication between V2 and MQ, for example, the resulting vector is still going to be 1 by 50. So nothing actually changes in between. All you're doing is you're adding something that is optimizable, so as to say, during backpropagation, but still preserving the dimensions. And this is where you introduce this query weights, key weights, and value weights. So now we convert these weights into essentially, to put it into neural network architecture or a neural network module, you can turn them into linear layers, like dense layers, with tunable weights. So we have a linear layer for query, we have a linear layer for key, and we have a linear layer for value. And after that, the module is pretty much simple. You do matrix multiplication between the outputs of the query weights and the key weights, which is pretty much similar to this, getting scores here. Now you're doing matrix multiplication because you don't want to do dot products over and over again for each word vector. So matrix multiplication takes care of that multiple dot products in one shot. And you weigh with softmax. And what you would do is you do matrix multiplication with these value weight, the outputs of the value weights, which is essentially similar to this y2 equals to w21v1 plus w22v2 plus w23v3. So that's pretty much it. That is it. This diagram is sufficient enough for you to go and use your favorite framework, whether it's PyTorch or TensorFlow, to implement self-attention mechanism on your own, or maybe even use NumPy if you want to. And the resulting vectors is exactly the same dimension as your input vector. Each of these vectors will have the same dimension as each of the vector in the input set. So I'm going to compare whatever that we have come up with right now with the original diagram in the Attention is All You Need paper. So in the Attention is All You Need paper, they have this thing called scaled dot product attention. They have two components, one scale and one mask optional. We're not going to talk about it right now. So if you remove these two boxes, we have Q's and K's, which are linear layer for query weights and linear layer for key weights. This edge coming out of the linear layer of key weights is a K, and the edge that is coming out of linear layer for query weights is Q. You do matrix multiplication, skips scale and mask for a while, and then you do a softmax, away the original words, and you do matrix multiplication with the edge coming out of linear layer of value weights, which is essentially this V. And that's it. That's your dot product attention. And remember, I have skipped the scale part, so I still cannot call it scale dot product attention. It's just dot product attention. Now we're going to put this scale in here. And this scale essentially is an element-wise multiplication with the with this number 1 over square root of dk. And dk actually refers to the dimension of your input word vectors. So what is the intuition behind this scaling? Imagine you have this vector a, 2, 2, 2. So it has an x component, y component, and z component. Let's just assume it's a three-dimensional vector. Let's find the magnitude of this vector. So it's essentially taking the square root of 2 to the power 2 plus 2 to the power 2 plus 2 to the power 2, which essentially is square root of 3 times 2 to the power 2, which essentially is square root of 3 times 2. If you divide this square root of 3 times 2 with square root of dk, where dk is 3 because 3 dimension, you basically cancel that square root of 3 with the denominator square root of 3, right? So you end up with 2, which is the average. So that's it. That's the intuition behind this scaling. So this is very important for cases when your vector is extremely high dimension, which is going to be the case because your input word embedding word vector is going to be 300 dimension, 250 dimensions, so on and so forth. So if you have a lot of dimensions, you're going to have a very big score. And you're going to weigh afterwards with the softmax function. So if you have a very big value that is going to the softmax function, that pretty much lies in the plateau region of the softmax function. So when you actually find the gradient of it, your gradient signal is going to be extremely weak that it's going to be pretty much useless. So this is a little ingenious thing that they stick it up in here, that is they scale the score in a way that score is a very well-behaving number, that when you find a softmax, it is a very well-behaving number in a good range. and when you find the gradient of it, it's going to have a good gradient signal. So that's pretty much it. That's the intuition behind this scaling thing. The whole diagram can be simmered down to this equation, which is something that you have seen in the paper. You do matrix multiplication between the q and the k. You scale it with the square root of dk. You take a softmax, and then you do a matrix multiplication with the v. That's the equation in your paper. And this is the scaled dot product attention. But in a sentence, when you're looking at a word, you're not just paying one type of attention. You're paying multiple attention to multiple things. To give you an example, if you see this sentence, I swam across the river to get to the other bank. Let's say you are looking at the word swim. The first attention that you might be giving is maybe to the river and to the word bank, because it's like swimming. So this is one type of attention you can have. The second other type of attention that you can possibly have is, where am I swimming to? You're swimming to the other bank, so to the other bank, you're paying attention to a different thing. Another thing that you might be paying attention to is like, who is swimming? I am swimming, like looking for a subject, or maybe just looking for articles. So if you use the single attention mechanism like this, then you're overtaxing these little blue boxes, these little weights, like for it to learn like subject, verb, object agreements, the grammatical correctness, the articles, and all sorts of things. And those little blue boxes may potentially become jack of all trade and master of none. That's not a very good thing. So if you have multiple things to attend to like that, wouldn't it be great to create a multi-head attention like this, where each attention head pays attention to a different thing? And that is pretty much what multi-head attention is all about. You have one attention head, you call this thing a head, and you stack them up. And stacking them up with different weights for queries, keys, and values so that they can learn different kinds of attention based on the task that you're asking the transformer network to learn. If you're doing a name entity recognition, these weights may learn different kinds of attention at each attention head. If you're doing some sort of autoregressive task where you're trying to predict the next word from the current word, these attention heads may attend to different things. Or if you're doing some form of sentiment analysis, same stuff, like these are going to attend to different things. But it is better than having just one attention head paying attention to everything. It is better to specialize these attention heads to do its task, which is better to have these attention heads specialize specific task. So it is going to produce a bunch of contextual representation sets like this. This y1 is not necessarily going to be similar to this y1, as this, for example, in this example, the word swam is going to be influenced differently in this schema where river and bank has a lot of weight on the word swam. But in this scheme, it's the word swam is going to have a different contextualized representation because it is more influenced by to the other bank. Here it is influenced by I. So these y's are not going to be the same, but at the end of the day, we want something which is exactly the same dimension as these v1, v2, and v3s. So, well, you might know what we do. We concatenate these vectors, and then we have another linear layer which basically reshape it into same dimension as our input vectors. So that is our beautiful multi-head attention mechanism. If you compare that to the original paper's attention is all you need diagram, this is the diagram from the paper. The idea is the same, and this diagram actually refers to this thing on the left. So this is attention is all you need papers, transformer architectures, multi-head attention. The video only focuses on that part. There's so many other pieces in this transformer architecture that is really interesting that I want to do a separate video to focus on these, which are positional encodings and the remaining bits and pieces of this encoder layers, the multiple encoder layers and decoder layers, and why it's a little bit different from the encoder layer, and then there's masked multi-head attention. If you remember, I skipped this thing called masked optional. This mask optional. This is going to be useful in this decoder, in which I will talk to it in a separate video. And notice how these little arrows are a little bit different here. So here it's like query, keys, and values are all the same source. In the decoder part, it's pretty much similar. The query, key, values are all from the same source. But in this case, the query and key is from the encoder, but the value comes from the decoder, and that's very interesting. And there's an intuition behind it, and then I will go into detail about it later on. So transformers with these multi-head attentions are used in NLP tasks these days, but that's not all. More and more we're seeing vision-related tasks using transformer architectures. This is a paper from Facebook. So they're using transformer encoders and decoders to replace certain mechanisms of object detection tasks like non-maximal suppression. They just take in the features from the CNN backbone and using these features as the input vector embeddings to these transformer encoders along with the positional encoding, because positional encoding, even though I haven't explained it before in this video, it's important because transformer doesn't know the order of the embeddings that it takes in, so you need to have some information latched onto these vectors to give the idea of like the order of the vectors, the input vectors. And essentially they're using this transformer encoder decoder to do the object detection task. And finally, there's a paper, anonymous paper in ICLR, which is still under review, which is called an image is worth 16 by 16 words. And they use transformers to completely replace convolutional neural networks completely. They just remove it and they use transformers to do like vision task. And on the right you can see multi-head attention, and you got 3 arrows. Basically this is query, keys, and values. Same idea of what I've told before. So that's the main point of the video. The purpose of this video is to give you the intuition of why self-attention mechanism is built the way it is built. Now you understand the components in this mechanism, and you see like there are certain weaknesses, there are certain things that you could possibly improve. So, you know, a person can ask, like, why do I need to understand all these things? I can just use the library, or I can just import a certain thing and then I can use a transformer as it is. I don't even need to understand any of this. Like, true, that is completely right. But there are researchers. If you're a researcher and if you want to advance this architecture, if you find like if you have a better idea that you want to experiment with, understanding these things from the first principles is extremely important. It is the bedrock of the advancements of the field of deep learning. You have to understand things from the first principle so that you understand the weaknesses, you understand why it is built the way it is built, so that you can read, even if you're not doing like some other new research, you can read papers with great intuition behind you, like, oh, now this paper is swapping this component out with this component, and well, this makes sense because because the older component has this kind of weakness. So that's my purpose. That's the purpose of this video. I hope you learned something from this video, and I hope you want to revisit if you have visited this transformer architectures and this attention mechanism before and had a hard time understanding. I hope you can revisit them right now with a better understanding.